Hey everyone, when you first use Docker, it just feels like magic, right? You type one command and boom, a whole environment just spins up in seconds. But it's not magic, it's just really, really brilliant engineering. And today we're going to pull back that curtain and break down exactly how that engineering works, from the kernel all the way up.
Okay, let's just get this out of the way right now because it's the number one thing people get wrong. If you've ever thought, oh, a container is just a smaller, faster virtual machine, hey, you're not alone. It's an easy assumption to make, but it completely misses the fundamental game-changing difference in how they're built.
And this lays it all out perfectly. Think about it like this. A virtual machine, over there on the left, is like building a whole new house from scratch. You need a foundation, walls, plumbing, electrical, a whole separate operating system. But a container, that's more like building a new apartment inside an existing building. It shares all that core infrastructure, the host OS kernel, which is why it's so much lighter and ridiculously faster to get going.
So how does Docker actually build that apartment inside your operating system? Well, this is where we get to the core secret. It's all about creating this incredibly powerful illusion of isolation around what is, at the end of the day, just a regular old process. And this is the main idea right here. You have to stop thinking about a mini computer. Instead, picture a single application, like a running Python script or a web server. Docker just wraps that one process in a set of virtual walls, basically tricking it into believing it has the entire machine all to itself. That, of course, is the million-dollar question. These walls aren't physical. They're not hardware. They are clever software constructs built from two core technologies that have actually been in the Linux kernel for a long, long time. So let's look at each one. The first building block for these walls is something called namespaces. You can think of this as perception control. It's all about what the process is allowed to see. So, inside its container, a process might think it's process ID number 1, the most important process on the whole system. But the host OS knows the truth. It's actually process ID, say, 5832. It gets its own private view of the network, of the files, of everything. It's kind of like putting a set of virtual reality goggles on the process, so it only sees its own little world.
Now, the second type of wall is built using Cgroups, which stands for control groups. So if namespaces control what a process can see, Cgroups control what a process can use. This is like its resource budget. You can literally tell a container, hey, you are only allowed to use one CPU core and you cannot have more than 512 megs of RAM. This is absolutely crucial because it stops one misbehaving container from sucking up all the system's resources and crashing everything else.
Okay, so we've got the process locked down. It can only see what we want it to see, and it can only use the resources we give it. But what about its files? An app needs its code, its libraries, all that stuff. Where does that come from?
This is maybe the most elegant part of Docker's entire design. See, instead of having one giant, clunky disk image like a VM, a container's file system is built up in layers using something called a union file system. It's an incredibly clever and efficient way to handle files. Let's see how this works. Basically, every single instruction in your Docker file creates a new unchangeable layer. So your from Ubuntu command, that's the base layer. Then you run a command to install Python. Boom, a new layer gets stacked on top with just Python in it. Then you copy your app code. You guessed it, a third layer gets added with just your code. And here's the best part. If you have 10 different containers running from this image, they all share those base layers. It saves a massive amount of disk space. The only thing unique to each running container is a tiny, writable layer right on top for any changes it needs to make. So we have this isolated process with a super efficient layered file system. But it's not very useful if it can't talk to anything or save its data for later, right? Let's check out how Docker solves these practical problems. Docker handles these two critical needs pretty elegantly. For networking, it creates its own virtual networks behind the scenes and basically acts as a little router, letting you forward traffic from your main computer to a specific port inside the container. And to solve the data problem, remember that writable top layer is temporary, it gets deleted when the container stops, we use something called volumes. A volume is just a way to map a folder on your actual computer directly into the container. It's like creating a permanent wormhole, so your data sticks around even after the container is gone. All right, we've broken down all the individual pieces of the puzzle. The process isolation with namespaces and Cgroups, the layered file system, the networking, the storage. Now let's put it all back together and revisit that first question we asked about virtual machines. And now, this table should make perfect sense.
Startup time is in seconds because we're not booting a whole new operating system. We're just starting a process. The resource overhead is super low because we're sharing that host kernel. And portability is just off the charts. As long as a machine has a compatible kernel, your container will run. The only real trade-off is isolation. VMs have hardware-level isolation, which is definitely stronger. But for the vast majority of apps out there, the process-level isolation a container gives you is more than enough security.
So to make sure this all really sinks in, let's do a super fast recap of the 3 pillars of Docker's architecture. First up, we have namespaces. This is what your process can see. It's the virtual reality goggles. Second, we have Cgroups. This is what your process can use. It's the resource budget, the allowance. And third, the union file system. That's the secret sauce behind those incredibly efficient, stacked up, layered files. And that brings us to the final and honestly the most important question. If we really internalize this idea that a container is not a tiny machine but just a single sandboxed process, it completely changes everything. It pushes us to build smaller, more focused microservices that do one thing and do it well. It changes how we think about our application architecture, our deployment pipelines, and our ability to scale. The technology is amazing, for sure, but its impact on how we think about building software, that is the real revolution.